Hi, this is Makbul Abdel with Pelion Device Management. In this video series, we're going to be walking through a tutorial on GitHub, and we'll be using the PSoC 64 secure microcontroller. In this first video, we're going to walk through how you set up the development environment and how you provision your board with credentials you need to connect to Pelion. Okay, so if you go to the tutorial on GitHub at this URL, and you scroll down to the README, and the first section is prerequisites, and we are going to be using ARM Mbed Studio. It's a desktop environment for building Mbed OS examples. And then we're going to install libusb for our debug interface connection and OpenSSL toolkit. And I will let you go through that information. I have already installed Mbed Studio on my system. And Mbed Studio is available for Windows, Mac, and Linux, so you should be covered on all your OS environments. In this tutorial, we're going to be using some Python tools that we'll install in our environment, and we're actually going to use the Python environment that comes with Mbed Studio. This Python environment is compatible and ready to use, so there's no need for an additional installation of Python. So to get access to that Python environment, go to Terminal, New Terminal, and then you should be good to go. So we can check the path to the Python installation with the which command on a Mac or where on Windows. And keep in mind, due to a known issue with Mbed Studio, if you close Mbed Studio and reopen it, you must close and reopen the terminal window. And then I recommend checking the path to the Python installation again to make sure that everything is set up correctly. Okay, the first thing we are going to do is import our example application. Go to File, Import Program, and we're going to select the same URL as our tutorial. It's easier if I just copy and paste it. And in my case, I have this imported a few times. I'm going to give it a unique name, and I will click Add Program. And this might take a few minutes depending on your system. And keep in mind that while Mbed Studio gives you the option to update all the sub-libraries in this example application to their latest version, we haven't tested them with the example application, so it's good to just keep them as they are. Okay, the next thing we're going to do in the tutorial is install Cypress tools. Now these are the tools that will help us with provisioning the secure storage of the PSoC 64 microcontroller. So we're going to open up our Python environment or our terminal, and we are going to type pip install CUI secure tools. Okay, so now we are going to provision our device with some initial credentials using those tools. And we're going to use a default policy file that comes within the Mbed OS file system. So first thing we're going to do is change our directory to that location using the terminal of Mbed Studio. So first I'm going to enter the directory of the example application. And then I will change the directory into the location of the policy file we want to use. And keep in mind that if you copy the path from the tutorial, that you might have to remove the top level application name from the path. So we're going to change that, and okay, now we're there. Okay, so now we're going to initialize the CUI secure tools. Give it our target configuration. And it's going to ask if we want to override what's there already, and we're going to choose yes. And then we're going to create some keys. And I'll talk about these keys later. These are for secure boot. Again, override yes. And then, okay, so now we are ready to actually provision. For this next section, we'll be doing two things. First, we are going to unplug the power, and we are going to remove jumper J26. And you only have to do this the first time you provision. So we're going to take that off, plug the power back in. And this is also the debug interface connection. And you want to make sure that the light is blinking. It blinks about 2 times a second, and that ensures that it's in the correct mode, which is called DAP-Link mode, and that has all the features we need for the rest of the lab. Okay, so now we have our board connected in the right mode, and we are going to launch another CY Secure Tools command. And this command is actually going to provision the device. It's going to set up the secure boot keys. It's going to set the security policy, and that'll give us the initial base provisioning that we need. Paste the command in the terminal window. And if this is your first time running this command on this board, you can run it as is. But if you're like me and you've done this a few times, you just add this to the command. So you add re-provision device, or you use re-provision device as the option instead of provision device. So I will run that. Okay, if everything went correctly, it should say provisioning passed or re-provisioning passed. Okay, if you have any trouble with this last step or any step, be sure to check out the troubleshooting tips in the tutorial. Now that the initial provisioning is complete, we're going to unplug the power. We're going to place jumper J26 back on. We're going to plug the power back in. Before we move on, let's take a step back and review what we just did. This is a very simplified, oversimplified view of what just happened, but it gives you a good idea of the main concepts. So imagine the secure storage within the PSoC 64 microcontroller is like a safe. And during the initial provisioning, we first set the security policy in that safe. And this controls things like which regions of the flash memory are accessible and for what purpose. Next, we generated a public-private key pair that's used in secure boot. The secure boot public key is then injected into the device, into the secure storage. And the private key will be used to sign user applications. So let's talk about the significance of public and private key pairs and what you can do with them and how we're using them in this case. So let's say you have two entities, and in one entity you want to create a signature, and the other entity you want to verify that signature. So let's say you have some data, could be any data. The first step is to calculate the hash of the data. Now the hash is a fixed size data that represents the larger data set. You take the private key and run it through a signature function. And I won't get into the math behind that, but essentially you get a unique signature that represents that data based on the private key. So then the second entity wants to verify that signature. So it has access to the data and the signature, and it also calculates the hash independently. So then it takes the public key, which is known to be associated with the private key, and it runs it through the verify function, and then it compares the output of the verify function with the hash data that it knows it should get after processing that signature, and then it can compare, was it valid or not. So with the private key, you can sign any data, and with the public key, you can verify, you can validate any signature based on that data. So how is this used in the secure boot scenario? So let's say you have your user image in a file, you want to generate a signature based on that user data, user image data, based on the private key, and that gets passed into the memory of the PSoC 64 secure microcontroller, and then it uses its public key that's embedded securely in the device to verify that the application is correct. Also with Secure Boot, it goes a step further. So you have a bootloader that is verifying the authenticity of the user application images, but you don't want anybody to tamper with the bootloader. And so there's an immutable boot code included in the PSoC 64 device that verifies the signature of the bootloader itself. So it boots up, it verifies the signature of the bootloader, and then the bootloader verifies the signature of the user application before it runs that. So you have a chain of trust, and you can have assurance that the device is running valid software. Also, to support unique identification and authentication per device, there's another public-private key that is generated on the device, and the public key is shared so that it can be used and bundled in certificates, and we'll talk about that later. And then the private key never leaves the device. For more information about provisioning PSoC 64, check out this guide at this link. For this part, we actually want to be in the top level directory of our example application in the folder called target CYTFM and so on. So you just need to copy this and jump up to the top level. Let's see where we're at. Okay, now we're at the top level and jump into that folder. Okay, next we are going to make a directory called certificates. And we're going to execute an OpenSSL command. And if OpenSSL is installed correctly, it should work. Okay, so basically what we're doing in these steps is creating a root certificate authority, and I'll talk about that in a little bit of why we're doing that. So the next thing we're going to do is configure our root certificate authority. So we're going to create a file called root.cnf and copy these contents into it. And you're going to do that inside the certificates directory that we set up. So I'm going to go to new file, root.cnf, give it a name, and then I'll open that file in the editor and we'll copy that, save it, and then move on to the next step. So we're going to create a certificate for our root certificate for our certificate authority. And we're going to use some default values as defined here, and we're going to pass in that file we just created. Let's just make sure we are at the correct directory level. Okay, again, if everything worked correctly, you shouldn't see any errors. Okay, the next thing we want to do is upload the root CA certificate that we just created to Pelion Device Management. And so the way you do that is go to Device Identity, Certificates, click on New Certificate, and then give it a name and select the file, and you want to select the .pem file. And it's very important you want to choose enrollment, and then click Upload the certificate. Okay, so the next thing we're going to do is inject our device certificate for Pelion into the secure storage using the provisioning tools. From that same target folder that we created the certificates folder in. We're going to launch the command again to initialize the CY secure tools at this point. And then we're going to run the create keys command again. And so these are going to be, going forward, going to be the important keys that you want to use. Basically, we're resetting the keys in the device. Okay, and then we are going to run this command from this location, and we're going to update one thing in the command line. So for demo purposes, we're going to be adding a serial number to make our device unique. And of course, in production, you would be bulk programming devices and give them unique serial numbers. So I'm just gonna 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and we're gonna run that, and it's going to reprovision the device, setting up the keys, and injecting our new certificate. Okay, reprovisioning passed. Let's talk about the Pelion Bootstrap certificate, which is what we just injected into the device. And again, this is an oversimplification, but it hits the main points. So this certificate is unique per device, and it allows Pelion to trust the device, and it's cryptographically signed by a certificate authority. And in this case, we generated our own certificate authority using OpenSSL. So how is this certificate formed? First, we generated the certificate authority, like I mentioned. It creates its own public-private key pair. And then we use provisioning tools to communicate with the device, which has its own public-private key pair. And then we made a request to get the public key from the device. The commands created a certificate signing request. So it basically takes information like the public key and other information about the device. It creates a certificate that basically embeds the public key, and then the certificate authority signs that certificate with its private key, and then that certificate gets sent back out through the provisioning tools and then injected into the device. Also, the certificate authority generates a certificate that has its public key embedded in it, and it's signed by its private key. And this certificate is called the Certificate Authority Root Certificate. So this basically will allow Pelion to verify signatures on the Pelion Bootstrap certificate that it receives from devices. So the certificate authority effectively proves ownership of the device's public key, which allows the device to be trusted by Pelion. Certificate authority root certificate, or also known as the factory CA certificate, gets uploaded to your Pelion account. So all your devices deployed in the field will all have their own unique Pelion Bootstrap certificates that can't be tampered with, and they are all cryptographically signed by the certificate authority that both Pelion and your devices trust. When they connect and register with Pelion, they present their Bootstrap certificates. Pelion calculates the validity of the signatures on the Bootstrap certificates using the certificate authority certificate that you've provided to your Pelion account. So with the Bootstrap certificates, now Pelion will trust your devices, and since they are unique and signed by a certificate authority, they can't easily be cloned. So now our device is connected and registered with the service, and in the next video, we'll talk about how to monitor its resources remotely and do firmware updates over the air. See you there.